Hi everybody, and welcome to the very first video of Math 200 Elementary Statistics. In this video, we will describe what statistics actually is. We'll also introduce a few terms to make sure that we know what we're talking about. We will talk about the possibly three classifications of data, and we will finish off with the 4 levels of measurement. So here we go. What is statistics? Well, it is the science of gathering and analyzing data to do one of 3 things, or a combination of 3 things. 1, to describe a situation, and we call this descriptive statistics. For example, we might have a collection of data. They could be all the adults in South Carolina, and we might want to know what their average height is, what the average age is, or average weight, how much they eat, whatever. Describing that situation is what we would call descriptive statistics. Secondly, we might want to estimate a parameter. For example, maybe that parameter will be the daily calorie consumption. That could be a point estimate where we actually try to estimate that particular number for the entire population, or it can be an interval estimate where we can say, well, we know we are 90% sure or 99% sure that the average value is between these 2 points. We would call that an interval estimate. And then finally, we would use this data to make decisions, and that is what we would call hypothesis testing. And how would that particularly work? Well, let's suppose you are trying to that you just designed a production procedure that produces 1-inch nails. Okay, and you want to make sure that it is doing this correctly. What you can do is you will test this using for over a certain period of time, collecting a variety of nails. You'll measure their length, and then based upon those measurements and the distribution of those measurements, you can use a technique called hypothesis testing to decide if process actually works to your specifications or if it does not. Okay, and this is where we start our nomenclature. The first term that we want to introduce is the idea of a population. And a population is the group of interest or the group under study. For example, if we are interested in the calorie consumption of every adult in South Carolina, our population will be, you guessed it, every adult in South Carolina. A parameter is a graphical or a numerical description of the entire population. So if you actually have something that represents the population in some way, that will always be a parameter. Parameters are always associated with populations. Now, as you might guess, it might be difficult to actually determine the calorie intake, or let's use something even simpler, the weight of every single person in South Carolina. There's probably close to 1 million people there. Actually, I don't even have an idea of what our state population is, but I know it's relatively high. The best that we can do is perhaps come up with a sample of all of those people in the population, and that sample will be the subset of the population, and we will use that sample to collect data. Now, there are a variety of ways to get that sample, to collect that sample. For example, I can use basically every single person who's watching this video. Would that be a good representation of the population? The answer would probably be no. Usually when we try to come up with a sample for collecting data, we like to use a sample that kind of transcends the entire population, and usually the best way to do that is through random sampling. But nonetheless, for the purpose of this course, a sample is nothing more than a subset of the population that is used to collect data. And the data that we collect and the data that we process or that we use to describe that sample are called sample statistics or just plain statistics. And they can either be a graphical or numerical description of the sample data. And we will use these statistics to estimate population parameters. Yes, I made a mistake. That should not say statistics. That should say parameters. And there we go. Much better. Now we can put what we just learned to the test. So here's our first example. And here we want to read the shortened survey report below and identify the population, identify the sample, and determine whether the highlighted value, namely this value right here, is a parameter or a sample statistic. Online gaming is gaining popularity according to a 2017 survey by Pew Research Center, but there are sizable differences by age and gender. The survey asked 3,930 U.S. adults if they play video games on a computer, TV game console, or a portable device such as a cell phone. And the report stated that overall, 43% of American adults say they often or sometimes play video games on one of the devices. However, those younger than 50 were almost twice as likely as those older than 50 to say that they play games. Basically 55% versus 28%. Okay, so notice what I have highlighted here. I have highlighted U.S. adults. They actually asked 3,930 U.S. adults if they play video games. Okay, so this right here is the sample of the population. So the population are U.S. adults. The sample is basically 3,930 of them. Okay, and then over here, their conclusion, which is something that they inferred from these samples, is that 43% of all Americans say that they often or sometimes play video games. So with that in mind, we can say that the population is all U.S. adults, that the sample is the 3,930 that participated in the survey, and since this describes the American adults or the U.S. adults, this is indeed a parameter because it describes the entire population. Okay, so let's just do one more example. And here it is. Once again, we are going to identify the population, identify the sample, and determine whether the highlighted value is a parameter or a statistic. In a 2015 National Telephone Survey about video games revealed that although both men and women play video games, men are more likely to refer to themselves as gamers. 50% of the men and 48% of women surveyed, so this is the result of the men and women that are surveyed, play video games. But men 60% were more than twice as likely as women, just 6%, to say that the term gamer describes them as well, or describe them well. The survey conducted by the Pew Research Center contacted 2001 adults 18 years of age or older living in all 50 U.S. states and the District of Columbia, either by landline, cell phone, telephone, or cell phone. So once again, the population is going to be all the adults living in the 50 U.S. states and D.C. Okay, that is the population, 18 years and older. The sample, right here, is basically just 2001 of them. And then is this a statistic or a parameter? Well, notice that this is a result of the people that were surveyed. In other words, this is a result of the sample. So this is a sample statistic, or just simply a statistic. So what do we have? We have that the population is going to be the adults in all, I forgot the end there, my bad, in all 50 U.S. states and the District of Columbia. The 2,000 adult, the sample are basically the 2,000 adults that were contacted in the study, and then this right here is a statistic because it is based upon the results of the sample. It is not based upon the population. It is not an estimate of the population. It is strictly strictly a result of this particular sample. Okay. So those are two examples that hopefully will give you some idea between the idea of a statistic, which applies to the sample, and a parameter, which applies to the population. As I mentioned, there are two types of statistics: descriptive statistics and inferential statistics. Descriptive statistics, try to say that 3 or 4 times 5, basically presents the data. It paints a picture. Specifically, it presents data in what hopefully will be a meaningful form. This can be in terms of a tabular form, such as frequency distributions, which will be the subject of the next video, or it could be a graphical form, which could be a bar chart, it could be a pie chart, it could be a histogram, or it could be a box and whiskers plot, which is actually what we have here. This actually is an interesting plot. This only applies to numerical data. This point right here is the lowest value in whatever data set you happen to collect. This point right here is the largest value in whatever data set you happen to collect. This right here, Q2, is what we call the median. It is the number in the middle. Now, it turns out that this box right here represents 1/2 of all the data in the data set. This over here represents 1/4, and this represents also 1/4. So it kind of gives you an idea of how close the data is to the median. The smaller the box, the more they're packed together, and this gives you an idea of what the total actual spread is. As mentioned before, it describes a situation or scenario and hopefully provides a clear picture. So once again, a descriptive statistics basically paints the picture or draws the picture. Inferential statistics interprets the picture. And specifically what I mean is it will take the picture and it will make judgments, or it will draw conclusions. Specifically, it will use the data to make some judgments about the population, and that could be in terms of a modeling, creating a mathematical model using something called regression analysis, which will probably be the very last topic we talk about in this course. Or it can be used to make decisions, which once again we will talk about later in the course. That's called hypothesis testing. Or it can be used to estimate population parameters in terms of either point estimates or interval estimates, which are also known as confidence intervals. Okay, so in this example, we're going to try to determine whether or not the statement is descriptive or inferential. Now remember, a descriptive statistic basically just tells you what it is. Okay, an inferential statistic interprets what it is to actually make a judgment or a conclusion. So here, AOL had 900 journalists, 500 of them at its local patch news operation. There's no judgment here. They're just basically telling you where 500 of them happen to be. That is descriptive. The next one, by the end of 2011, Bloomberg expects to have 150 journalists and analysts for its new Washington operation, Bloomberg Government. So here, we are making a prediction. We are making a judgment. We're not describing a situation. We're describing what we think is going to happen by the end of 13 years ago. So this right here is inferential. Next, we have data classifications, and there are two general classifications. One is qualitative, which are just labels or descriptions or qualities. For example, favorite topping on a pizza, pepperoni, mushrooms, onions, whatever. Those are labels, those are descriptions. Favorite color, same thing. They are just strictly qualities. Whether you'd finished first, second, or third. Now, we could label those as 1, 2, 3, which by the way are numbers, but they are qualitative because they are just labels and they are just descriptions. Quantitatives consist of counts or measures, or they're specifically quantities, like the height of all the doors in the building, the number of doors in the building, the number of shades of red. Those are all quantities that can either be measured or counted. So keep in mind that and clearly a quantitative classification will always be a number. However, a qualitative classification can either be a label or it can be a number if that number is being used as a label. So just because you see a collection of numbers, just don't immediately think they're quantitative. If those numbers basically map to a description, map to a label, then that happens to be a qualitative assessment. For example, when you have a survey where you You're asked a certain questions and you have the answer between 0 and 5, where 5 is most agreeable and 0 is least agreeable. That's a qualitative assessment. That is not a quantitative assessment. Those are not counts. Those are not measures. Those are labels. So it's important to be able to tell the difference between one and the other. So here's a quick example to get an idea of what we're talking about here. So we want to classify the following data sets, I think there's 4 of them, as either qualitative, in other words, labels, or quantitative, counts and measures. The shades of red paint in a home improvement store. Okay, well, those will specifically be different. So shades of red: pink, ruby, light pink, fuchsia, whatever. Those are all indeed labels. That is qualitative. The rankings of the most popular paint colors for the season: first, second, third, fourth, fifth. So once again, those are labels for preferences. That also is qualitative. You'll never guess what the next 2 are. Okay, the amount of red dye necessary to make 1 gallon of each shade of paint. So that actually is going to be a measurement. That is going to be 1, 2, 3, 4, whatever millimeters of dye you need to get the appropriate shade. So that is quantitative. And then finally, the number of paint choices available at several stores. Those are counts. 1, 2, 5, 10, 20. Nowadays, probably a couple of thousand. It's amazing the colors that people can come up with. But once again, that is qualitative. Okay, now so we have quantitative and we have qualitative data. Qualitative data obviously is discrete. Quantitative data can be measurements or counts. Now typically, if the quantitative data is a measurement, it will be continuous. Not always, but usually. Okay, which basically means it can take on any value within a given interval. Let's just talk about, for example, height of a college freshman. It could take on any value as low as 4 feet, hopefully not lower, and as high as 8 feet. I think I had a couple of 7-footers in here a couple of years ago. And it can take on any value in between 4 feet and 8 feet. For example, I could come up with 2 numbers that I think are really, really close together, and there is going to be and if I do that, there will always be a number that's possible in between them. And that's the idea of continuous data. It can take on any value within a given interval. And the other one is discrete. It can only take on certain values. They are what we would call, in mathematical terms, countable. 1, 2, 3, 4, 5, 6. The number of Grammys Taylor Swift won. You can go all the way up to infinity, but there will always be a countable number of values. And that brings us to this example: continuous or discrete. The temperature in Fahrenheit of the cities in South Carolina, that can go as far as, very sporadically, down to 0 degrees Fahrenheit, sometimes a little lower, all the way up to well over 120, and any possible value in between. It's a measure. Chances are it's going to be continuous, and it is. The number of houses in the various neighborhoods of cities. Well, we can count houses. Those are counts, and we can count them. 1, 2, 3, whatever. In my neighborhood, the number of houses, well, actually, I don't know the number of houses. The number of lots is 436, but nonetheless, those are discrete. The number of elliptical machines in every YMCA in your state. Now, frankly, I don't know. But I do know that we can count elliptical machines. We are talking about counts. They are typically discrete, and this one is discrete as well. And then finally, the height of doors, a measurement. And the height of doors can be as low as, 3 feet for a doggy door, maybe 2 feet for a cat, all the way up to 8 or 10 feet, whatever, and it can take on any number, any possible value in between. This would be continuous. And this brings us to our last type of measurement, or last thing that we need to talk about, and that are levels of measurement. And there are 4 of them. You'll notice that nominal ordinal will correspond to qualitative data, and you would be correct. And then interval and ratio would correspond to quantitative data. And you would be correct there as well. So but let's first go ahead and talk about nominal. Nominal is strictly labels or names. This is going to be qualitative data. There's no way to compare one to the there is no implied ranking. For example, favorite pizza topping or pizza topping in general. There's no way to rank pepperoni and sausage. Well, actually, I could. I think pepperoni and sausage is a hell of a lot better than onions or peppers, but that's just my preference. But there's no way to there's no implied ordering there. If I was talking about shades of paint, the exact same thing. The exact same thing there. The type of chair. Once again, there is no implied ordering. And as I mentioned, there are some of those. There are some of the examples right there. Let's not forget our favorite number. Now, if you have qualitative data and there is an implied ordering, then we have the ordinal scale, which kind of makes sense. Ordinal, ordering, kind of makes sense. And these can be arranged in a meaningful order. However, calculations with these do not make sense. For example, here is the airplane seat assignment. 1A would have 1A and 2F probably have a more favorable order than, say, 33B. In other words, now this, of course, we know this is basically the middle seat in the last row of a plane. So once again, at least to some people, this would have an implied meaningful order, and obviously this also has a meaningful order. Now, if it turns out that addition and subtraction makes sense, then we have what we call an interval level of measurement. This will always be quantitative. Okay? They can be arranged in a meaningful order. However, the differences between the data entries are also meaningful. For example, temperature in Fahrenheit. Clearly, 32 degrees is a lot colder than 80 degrees. Okay? And if is a lot colder than 80 degrees, and 40 degrees is also colder than 80 degrees, then warmer than 32. And the differences actually have some meaning. Obviously, 42 minus 30, I'm a little bit warmer. Or 40 minus 32, I'm a little bit warmer. 80 minus 32, I'm a lot warmer. There is some difference here. The only thing you have to be careful about is the fact that in interval measurements, 0 or interval level measurement, 0 really has no meaning. It is just a placeholder. For example, 0 degrees Fahrenheit, that's just a placeholder. It means there is no particular meaning behind it. It is just where we happen to map 0 to. 0 degrees Celsius. Of course, that corresponds to the freezing temperature, the freezing point of water, but nonetheless, that is just a placeholder. And why is that important? Well, you'll understand that a little bit better when we talk about the last level of measurement. But once again, temperature in Fahrenheit, temperature in Celsius are examples of an interval level of measurement. The birth years of your classmates, also an interval level of measurement. Clearly, if you were born in I was born in 1960, you guys were probably born in about 2001. Clearly, I'm older by a lot. Okay, and that brings us to the last level of measurement. That is ratio level of measurement. Once again, it is quantitative. It can be arranged in a meaningful order. The difference between the data entries are meaningful. However, the 0 point represents the absence of something. For example, the example that I want to continue on is temperature. Remember, Fahrenheit, 0 is a placeholder, somewhere below freezing. Celsius, once again, 0 is a placeholder. It is basically mapped to the freezing point. However, as accordingly, those are interval interval levels of measurement. Temperature in Kelvin is a ratio level of measurement. Why is that? Because 0 degrees Kelvin represents the absence of thermal energy in a molecule. An example of ratio scale might be the horizontal distance that a bottle rocket travels. If it is 0, it's the absence of distance. It didn't go anywhere. Okay? Or the age of all the resonance in Gaffney. For example, if I'm 10 and the other guy and somebody else is 20, or well, I'm 61. If somebody else is 30, obviously I'm twice as old. So these correspond to ratio levels of measurements. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Oil, signing off.